Okay, hi. So in this video, we're going to have a look at velocity time graphs. In the last video, we had a look at distance time graphs, but you also need to know how to draw and how to interpret a velocity time graph. Now, I'm just going to scroll down quickly because the first thing we need to know is what velocity is. All right. So velocity and speed are often confused. Now, velocity is speed in a given direction. All right, and that actually makes it different to speed, because if you were traveling at the same speed but you were changing direction, then you are actually changing your velocity because your direction has changed, and velocity takes into account direction and how fast you're going. For that reason, it means that we can actually have negative velocities. If you take one direction to be positive and then you go in the opposite direction, your velocity is actually going to be a negative value. Whereas with speed, you cannot have a negative speed because there's no way that you can travel at minus 10 miles an hour in terms of speed. Okay, you're either traveling 10 miles an hour or you're not. But with velocity, you can be traveling minus 10 miles an hour or minus 10 meters per second. All right, so that leads us on to the next quantity, which is acceleration. All right, acceleration. Now again, this is often confused as the change in speed, but that's not actually true. Acceleration is the rate of change of velocity. Okay, rate of change of velocity. So it's how fast your velocity is actually changing, right? And we can think of that in terms of a formula. You could say that acceleration, all right, is equal to your final velocity, so the velocity you end up at, take away the velocity you start at, and then divided by how long does it take for that to happen. All right, so in this case, A is equal to acceleration, V is equal to final velocity, U is equal to initial velocity, and t is equal to time taken. Okay, that's the time taken to go from your initial to your final velocity. All right, and so let's do a quick example just to show you how that works in real life with a real problem. Let's say, for example, you are traveling at a velocity of 8 meters per second. Okay, 8 meters per second is your velocity. You then accelerate. All right, and you end up at a final velocity of 32 meters per second. 32 meters per second. All right, and that actual change in velocity takes you a grand total of 10 seconds. Okay, so what is the acceleration? Well, 8 meters per second, that is u. Your final is v, which is 32 meters per second, and your time is equal to 10 seconds. So all we're going to do is we're going to say that acceleration is equal to final v minus initial u divided by time, which is 10. That gives us 32 take away 8 is 24. 24 over 10 gives us a grand total of 2.4 meters per second squared, or meters per second per second. All right, both of those are the same thing. They are the units of acceleration. All right, and so let's now have a look at how this can actually be seen on a velocity time graph. So what I've done is I've plotted in some points and I've broken down the graph for you. And so when you have a graph like this, all you need to do is join the points. Now, this is not going to be a line of best fit. This line has to go exactly through all of the points. All right, and so the first part is a straight line like so. I know it's not perfectly straight, but it's close enough. With a ruler, obviously, you would be drawing this perfectly straight. Now, in part B, we also have a straight line from here to here. Okay, then in part C, we have a straight horizontal line like so, and then in part D it goes all the way back down to the bottom. All right, now what we have on the y-axis is the velocity, and on the x-axis, let's scroll down slightly so you can see it. There we go. On the x-axis is the time. Okay, now there are certain things for us to realize on this graph. All right, so in the first 15 seconds in part A, What's happening is we are accelerating. Now, a straight line on a velocity time graph that isn't horizontal means constant acceleration, all right? So this means that we are constantly accelerating, okay, from 0 meters per second to 15 meters per second, right, which we can see here. That takes us a grand total of 15 seconds, right? We can do calculations with that in a little bit. In part B, we are accelerating constantly again. You can see that the line is more shallow, and so we're accelerating from 15 meters per second to 20 meters per second. That takes us a further 15 seconds. In part C, it's a completely horizontal line, which means that the velocity doesn't change. And if the velocity doesn't change, then there's no acceleration. So part C is traveling at constant velocity. All right, now part D, the line goes down. Okay, so our velocity decreases from 20 meters per second to 0 meters per second, and that takes 10 seconds. All right, so from 40 to 50. That is what we call a deceleration, or you could call it a negative acceleration. All right, if a line is sloping downwards, then it is a negative acceleration or a deceleration. Okay, now what I'm going to do for each part is I'm going to work out the acceleration. And you'll see exactly how to work out the acceleration on any velocity time graph. The acceleration is basically the gradient of a line. When it's a straight line, that makes things pretty simple because we can just use our equation. Remember from before, our equation is acceleration is v minus u all over t, right? And this is actually how you find out the gradient of a line, right? In maths, you take a point and you do the final y-coordinate minus the initial y-coordinate, and you divide that by the difference between the x-coordinates, right? And that's what this is here. So for part A, our initial is 0 and our final is 15, okay? So I can just replace those. The final was 15 meters per second. The initial is 0. And how long does it take us? Well, it takes us between 0 and 15, which is 15, okay? So acceleration is I'll do it above, is 15 over 15, giving us 1 meter per second. All right, that's the acceleration in part A of the graph. Now part B, how about you pause the video now and try and have a go at the acceleration for part B. All right, now I hope you had a go. Well, we're going to do exactly the same thing again. So acceleration is equal to, now the final velocity is 20, so it's 20 minus the initial velocity, which is 15, as we can see there, 15, okay? And that takes how long? Well, it's between 15 and 30 minus 15 is 15, okay? So if we sub in the numbers, 20 minus 15 is 5, and on the bottom is still 15, so it's 5 divided by 15, which equals 1/3 basically, but we're going to quote that to 2 decimal places as 0.33 meters per second. Meters per second squared, and that's for both of those because it's an acceleration, not a velocity. That's my mistake. So meters per second squared. Now part C. Now the initial velocity is 20 and the final velocity is 20. So our acceleration is equal to 0 minus 0 over, how long does that take? 10 seconds. Well, 0 minus 0 is 0, and 0 divided by anything is still 0, so our acceleration is 0 meters per second squared. Alright, and that makes sense because it's a horizontal line, and remember I said for a horizontal line there's no acceleration. Alright, lastly, for part D, we can see that our final velocity is 0, right? But we don't change the formula. The formula will remain exactly the same. So A is equal to final velocity, which is 0, because it's 0 here at the end, minus initial velocity, which is 20. All right, so minus 20 over, how long does that take? Well, between 40 and 50 seconds is 10 seconds. All right, that will give us an answer of negative 20 over 10, which equals negative 2 meters per second squared. And you can see how that actually has a negative answer. That's because it's a deceleration, right? Because you're slowing down rather than speeding up. Okay, and so therefore we've actually calculated the acceleration for all 4 parts of that graph. Now let's rub those workings out. Because there is one final thing we can work out from a velocity time graph, and that is how far we have travelled, alright? And it comes from the equation that speed is equal to distance over time, alright? Which means that distance equals speed times time, alright? Now, in this case, we swap speed for velocity, okay? For velocity, because velocity is speed, but in a given direction, right? Now, why is that important? Because it means that if we were traveling, let's look at C, okay, if we're traveling at constant speed or constant velocity in this case, right, if we multiply our velocity, which is 20, okay, by the time, which is 40 minus 30, which is 10, so the time there is 10, and the velocity is 20, okay, you can see that we get the area of this rectangle. Okay, because it's 10 times 20. And that will give us our distance. And that works when you have constant velocity. When you don't have constant velocity, what we are still going to work out is the area under the graph. But because if we have a line with a gradient like so, we wouldn't be working out the area of a rectangle anymore. This, to me, looks like a right-angled triangle. Part B, to me, looks like a trapezium. Okay, and part D looks like another right angle triangle. Okay, so we can work out the distance on each one. Now, I'm going to do C to start off with just because it's the easiest. So we have 10 seconds there multiplied by 20, which will give us a grand total of 200. And because the units are meters and seconds, right, and the seconds cancel each other out, it's meters. Notice that if velocity was given in miles per hour, then your distance would have been in miles, not in meters, all right? But we are working in meters, and so that's fine. So there we go. Okay, now let's have a look at A. Well, A, you've got this right angle triangle here. And our velocity is 15, and so the height is 15. And on the bottom, we go from 0 to 15, and so that is 15 as well, all right? And so what we're going to do is to work out the area of a triangle, it's half times base times height. And that is going to be a half times 15 times 15. Well, 15 times 15 is 225, and you half of 225, you'll get 112.5. And so that is 112.5 meters. All right. Now let's have a look at D, because it's going to be slightly simpler than B, sorry. And so the height there is 20, okay, 20, and the base is 10, okay, because it's between 40 and 50. So again, I'd use half base times height, right, but the base this time is 10, so it's a half times 10 times 20, which equals 200 times a half, which equals 100 meters. All right, so 100 meters are traveled in part D of the journey. All right, now finally, part B. Now, part B is slightly more tricky to work out. But the easiest way to do it, really, is to split this into a rectangle and a triangle. And the way we can do that is just by cutting it there. Okay, so where the flat line is, this makes a right angle triangle here, all right, which we can work out the area of, and then we can just work out the area of this rectangle here. All right, so that's what I'm going to do. And the rectangle at the bottom has a length of 15. It's actually going to be a square, isn't it? Because it's 15. And the height is also 15. All right, so it's 15 times 15, which makes this square part here 225 meters, because it's just 15 times 15. Now, finally, I have a look at this triangle here. And it is 15 across again. So it's 15 across. But the height is between 15 and 20, which makes that 5. All right, 5. So what we do is the base is 5 and the height is 15, say, if we tilt it up the other way. And so we do a half times 5 times 15. All right, well, 5 times 15 is 75. 75 over 2 is 37.5, or 37.5 meters. So 37.5 meters for that top part. All right, now let's rub out these numbers here, just so it's a bit more clear. So in total, all right, all we'd do is we'd add everything together. So we'd say our 200 plus our 100 plus our 225 plus 112.5 plus 37.5, and that would give us a grand total. We do 200 plus 100 plus 225, and that's going to give you 525, and then 112.5 plus 37.5 gives you 150. So that will give you 525 plus 150, which makes 675.0 meters. Okay, so in total, this whole journey, you travel 675.0 meters. All right, and that is going to bring me to the end of this video, because what we have done is we've learned how we draw velocity time graphs and what they show, how we work out acceleration, and how we work out the distance traveled. All right, and all of those things you need to be able to do from a velocity time graph. There are more things you can do with a velocity time graph than a distance time graph, because with distance time graphs we can't work out the acceleration. We can work out the speed. If it was a displacement time graph, we could work out the velocity, but you can't work out the acceleration. All right, and so that brings us to the end of the video. Please like and subscribe as per usual if you did enjoy the video, because it does really help me out. But if you do have any questions or you're still struggling, please feel free to send me a direct email using the link below, or post a comment and I'll be sure to get back to you. But I look forward to seeing you in the next one.